Welcome back, guys, to the Astronomy Week organized by Astro Club of Fergusson College. My name is Ansh Dabkara, and today we are going to talk about stars and sun. So, a basic question arises in our mind that why we are studying stars and sun. Why are stars important to us? So, according to Big Bang theory, at the beginning of the universe, the only elements that existed with hydrogen, helium, and lithium are stars. All other natural occurring elements were formed during the life and death of stars. And we all know that our sun is a star. So that's why our stars and sun worth studying. So, guys, fasten your seatbelts. We are going to travel millions and billions light years away from here. So first of all, we are going to understand what is interstellar medium. So interstellar medium consists of interstellar matter, which are several hundred parsec from here. So a parsec is a unit which is equal to 3.26 light years. So basically, interstellar matter is millions of light years from Earth. So now, what is interstellar matter? Interstellar matter is the matter and radiation which exists in the space between the stars and system of galaxies. This matter includes gas in its ionic, molecular, as well as in atomic form, and it also consists of dust and cosmic rays. So, in interstellar medium, there are different regions of density, temperature, and different composition is there on interstellar medium. Moving towards giant molecular clouds, these giant molecular clouds are present in interstellar medium, which is made up, and these clouds are made up of dust and gas particles in their ionic and atomic form. It also consists of some cosmic rays and radiations, due to which there are S2 regions occur in these molecular clouds. So, what are these S2 regions? So, these are typically a cloud of partially ionized hydrogen gas. Due to this S2 regions, the destruction of giant molecular cloud occurs into parts, and these parts are known as clamps. So, due to S2 regions, these clamps are occurring on giant molecular clouds. These molecular clouds are dark and dusty clouds, and these are responsible for the formation of star. Now, for understanding the process of formation of stars, we first need to understand what is virial theorem and how this virial theorem is applicable to the molecular clouds such that they are converted into stars, and how these clouds are converted into stars we will understand via virial theorem. So this Virial theorem is applicable for stable and self-gravitating spherical discrete particles, or we can say point mass particles which are stable and which have self-gravitational force. So this Virial theorem provides a general equation that relates the average overtime of the total kinetic energy, which is equals to half of its potential energy of the system. So, due to this virial theorem, every discrete particles which obey this virial theorem are in virial equilibrium. So, like for example, a star in a galaxy, galaxies in a cluster, planets and its satellites. This all are in virial equilibrium and following the virial theorem. So this equation represents virial equilibrium free fall time equation, which is half dabba square I by dabba t square is equals to 2t plus 2u plus w plus m. Here w is gravitational potential energy, which is a negative quantity. So basically we need this equation to fulfill our two conditions, which gives us the information that how these molecular clouds are converting into stars. So now, moving towards our first condition. So now we will move towards the first condition, which is 2 into t plus u is equals to 0 and m is equals to 0. By substituting this value in our initial equation, we will get the free fall time, which is equals to 3 pi upon 32 g into rho to the power minus half. Here g and pi are constant, and rho, so this whole value depends on the density of the molecular cloud. So as per the relation, if the density of molecular cloud is more, then the time taken by the cloud to free fall in itself is less. So basically, this equation is giving us the free fall time that how much time is taken by the cloud to gravitationally collapse in itself. So why the cloud is collapsing in itself, how it happens, and what are the conditions such that the cloud is collapsing in itself? We'll look further. So this second condition is the criteria for gravitational collapse, and the condition is 2 into t plus u plus w is equals to 0. By substituting this value in our initial equation, we can find the length and the mass by the Virial equation, and this length and mass is calculated by Professor Jeans. So this is known as gene length and gene mass. So gene length is 0.19 times per sec into T upon 10 Kelvin to the power half into concentration of H2 region upon 10 to the power 4 centimeter per cube to the power minus half. So this length is giving us the radius of how much from the center of the giant molecular clouds, how much radius it will cover such that this cloud collapse in itself. And gene mass is giving us the mass which if the cloud exceed, it will collapse in itself, which is equals to which is equals to 1 point mass of sun into T upon 10 Kelvin to the power 3 by 2 concentration of H2 region upon 10 to the power 4 per cubic centimeter to the power minus half. So when a cloud mass exceeds the gene mass, it collapses in itself. तो अभी अपने आप तो होगा नहीं कि क्लाउड का मास बढ़ जाएगा जीन मास से, कुछ ना कुछ तो होगा. So there are some triggering conditions due to which the cloud mass is exceeding the gene mass. So there are basically two triggering situation. The first situation is supernova. So supernova is basically a explosion, a big explosion due to which mass is released in form of matter, and this mass is acquired by the cloud. So when the cloud acquires this much of mass, it stores in clamps, and the mass exceeds from the gene mass, and the cloud gravitationally collapses in itself, and the process of star further continues. And the next situation of this triggering possibility is when the two galaxies collide, they produces a shock. This shock exerts radiation in matter, due to which this matter in form of mass consumed by the molecular cloud, and due to which the molecular cloud mass exceeds the gene mass, which is calculated by the Virial equation, and it gravitationally collapses in itself, and process of star continues. So these are the two situations: the supernova explosion and the colliding of galaxies are the triggering situation due to which the gravitational collapse of clouds are occurring. Okay, so till now we know that why this giant molecular clouds are gravitationally collapsing in itself. So now we are ready to understand the process of uh, star formation from dark cloud to the main sequence star. So in this picture, there are several stages from A to F, from dark cloud to main sequence star, how the star formation is occurring. So in stage A, the dark cloud, which is giant molecular cloud, has some clumps, as you can see that in A stage. So these clumps are due to destruction of asteroism in the molecular cloud. So basically, these clumps acquire mass in form of matter from the triggering situations from the surroundings, and it when this mass exceeds the gene mass, it started collapsing in itself. So when it starts collapsing in itself, it loses its size. So basically in stage A, the size is 2 lakh astronomical unit, and in stage B, which is pre-stellar core, the size becomes 1000 astronomical unit. So the process of collapsing the cloud in itself continues to stage B, and from here our time starts. So at t is equals to 0, the size of the molecular cloud is 10,000 astronomical unit, and this stage is known as prestellar core. Prestellar cores are the nurseries of new stars and an early phase in the formation of low mass stars. Before the gravitational collapse produces a central protostar, prestellar core is the stage. So basically, why pre-stellar cores are known as nurseries. So pre-stellar cores helps us to understand large-scale physical processes which are dictating star formations by the properties of pre-stellar cores. Now, moving towards stage C, which is protostar. When pre-stellar collapses in itself in the center, protostar forms. A protostar is a very young star that is still gathering mass from its parent molecular cloud, and it is the earliest phase. This phase begins when a molecular cloud fragments first collapses under the force of cell gravity and an opaque. It ends when the infalling gas is depleted. So it ends when the infalling gas is depleted. This protostar again collapses in itself, and during this, the time of 10 to 100,000 years takes, and the size also decreases to 1,000 astronomical unit. When the protostar gets smaller, it is in spin faster because of conservation of angular momentum, and an increase in pressure and increase in temperature took place. So basically, when protostar is formed, nuclear fission begins, and this leads us to the stage D, the T-Tauri star. The T-Tauri star is a class of variable stars that are less than about 10 million year old. This class is named after the prototype T Tauri, a young star in Taurus forming region. The T Tauri star are pre-main sequence star in the process of contracting to the main star. So basically, this is T Tauri star is an intermediate process between the pre-main sequence star to main sequence star. This T Tauri star is occurring to spin due to since the protostar is smaller. Thus, it takes millions of years for the core to rise its temperature to start the nuclear fission, igniting the core and setting up to the longest stage of the star, which is the main sequence star. So from the pre-sequence star, the conversion of main sequence star taking place. Pre-main sequence star is an earlier stage of main sequence star. In it, when a protostar that grows up acquiring mass from its surrounding envelope of interstellar dust and gas, and due to this gathering of mass, it collapses. The collapsing process is continuing, and the protostar is converting to main sequence star, and later this pre-main sequence star is converted to the main sequence star. This main sequence star is the longest journey, or we can say the middle phase of the star, and here formation of star completes. Now, after the formation of the star, how do we classify this star into different genres? So, how do stars differ is explained by Hurtzsprung Russell diagram, or which is also abbreviated as HR diagram. So, HR diagram is basically a scatter plot of stars showing the relationship between the luminosities versus the effective temperatures, and spectral class versus absolute magnitude. So it is a tool to classify stars according to their luminosity, their spectral type, their color, their temperature, and their evolutionary stage. So at x-axis, you can see that along with the x-axis, the temperature is decreasing, and along with the y-axis, the luminosity is increasing. So now we will talk about the graph. First of all, you can see that the horizontal branch is main sequence star, the stable middle phase line, which is undergoing nuclear fission and converting hydrogen to helium. So this is the middle, or we can say young life of star. Now moving towards right upper side, we get here giants, which has temperature range from 5,000 to 3,000 Kelvin, and luminosity of 100 to 10,000 luminosity unit. So towards the right of the plot, it shows us the giants, which is also known as red giants. They form from low mass stars after the hydrogen fuel is exhausted, and they are relatively cooler than main sequence stars, but show more luminosity than main sequence stars. They are enormous in size. red giants are converted to white dwarf when the fuel gets exhausted and all hydrogen and helium is over. Now going towards the left corner in the plot, left down corner of the plot, we got white dwarfs. These white dwarfs are basically when the red giants have exhausted their fuel, it converts into white dwarfs. Uh, Moving towards top upper right corner of the graph, we see that there are supergiants. These supergiants are enormous in size and they are at the top right region, which means it has a highest luminosity and low temperature range. Their radius is greater than 1,000 times that of our sun. Yes, the radius of supergiants are 1,000 times that of the sun, and that's why they are important for our study. They are formed from large main sequence stars. Apart from all this, you can see that in between we have instability strips which contain several classes of variable stars. So here is a quote of a star which is well known. More the enormous the mass of a star, more the energy it produces. Yes, it's true. So जितना ज़्यादा स्टार बड़ा होगा इतना ज़्यादा उसमें मास होगा उतनी ज़्यादा वो एनर्जी रेडिएट करेगा और उतनी लाइफ उसकी कम होगी. So now on the basis of HR diagram, we can show the classifications of a star based on their color and temperature range. So as you can see in the chart given, class O has color blue with surface temperature about 30,000 Kelvin, and as the trend going downwards, temperature decreases and the color changes to red. So class M has color red with surface temperature less than 3500 Kelvin, and intermediate stage is with color yellow, the class G, with surface temperature 5000 to 600 Kelvin. And in this class, our star, our very own galaxy star, solar system star, Sun exists. So we can say that our Sun is basically a G-type main sequence star, a G-type class main sequence star. And by looking towards the trend of the chart, we can convey that blue has highest temperature and red has the lowest temperature. So with the color blue, the temperature is highest, and with the color red, the temperature is lowest. So at this point, we are ready to summarize the whole life cycle of stars. As we have seen the previous slides, the formation, the classification of a star. So now we are ready to give a basic summary of how the star formation is occurring and how its death is occurring. So first of all, birth takes place inside a hydrogen-based dust cloud called nebula. This nebula is basically the part of giant molecular dust cloud. This giant molecular dust cloud, when mass exceeds from the gene mass as calculated from the Virial equation in the previous slides, it collapses in itself, gravitationally collapses in itself, and is converted to a protostar. This protostar, again by collapsing process is continuous in itself, it converts into the main sequence star. Now, when this main sequence star has low mass less than 1.4 solar masses, and its fuel gets exhausted, it will convert it into a red giant. This red giant we have talked in this about this red giant we have explained in HR diagram. So now when this red giant, the hydrogen and helium is also converted fully, and the fuel is exhausted, it converted into white dwarf, and when white dwarf has no luminosity, it converts it into black dwarf. Now, what if main sequence star has intermediate mass? It will convert it into a neutron star when fuel is exhausted. And what if main sequence star has high mass, more than 3 solar masses? It will convert it into a black hole when the fuel of main sequence star is exhausted. So the similar process can also be done by when the supernova explosion is there. So this all is a brief summary of life cycle of our star, how the star form and how the star is ended. And in the end, for understanding more accurately, these are the endpoints of star life. So basically, what is happening when in a star, when nuclear fusion is completed, the fuel is exhausted, the star die. The star die, it means the star is converted into another entity. So first of all, if the mass of a star is less than 1.4 times the solar masses, the considered in the series of low mass star, and after the fuel exhausted, it converts into white dwarf star. Second, when the mass is greater than 1.4 times the solar masses, it is considered in the series of intermediate star, and it is converted into neutron star after the fuel is exhausted. The third, when the mass is greater than 3 times of solar masses or more than 3 times of solar masses, it converts into a black hole. Yes, guys, when mass is greater than 3 times the solar masses, the star and life is black hole. So this is all about our stars. I think it is much interesting and very knowledgeable for you. So now we will move further to our next topic. So now we are going to learn about hot ball of glowing gases. So guys, turn on your air conditioner. It's going to be hot here. So our sun is hot ball of glowing gases, and our sun is a G-type main sequence star at the center of our solar system. It is nearly perfect sphere of hot plasma, and it is by far the most important energy source of life on Earth. Basically, 1 million Earth can fit inside the sun, and it holds 99.8% of solar system mass individually. It is said that approximately 10 billion years is the age of Sun, in which 4.6 billion years is completed. Sun is orbiting 25,000 light years from the galactic core, and its temperature is approximately 5,500 degrees Celsius. So it is currently fuses about 600 million tons of hydrogen into helium every second, and it means it is converting 4 million tons of matter into energy in every single second. Thus, it is important as for understanding the structure of Sun. So, basically, structure of Sun consists of six layers. The first layer is inside the Sun, which is core. The second is radiative zone. The third is convective zone. The fourth is photosphere, and the fifth is atmosphere. And the sixth is basically not a layer. It is a covering which is known as tachocline, which is separating radiative zone and convective zone. Okay, so now we will discuss briefly about the different layers of sun. Starting from the innermost layer, which is core. The core of sun extends from the center to about 20 to 25% of the solar radius. The temperature of core is approximately 15.7 million Kelvin. Yes, the temperature of core is 15.7 million Kelvins. But sun surface has approximately 5800 Kelvin temperature. The core is the only region in the sun that produces an appreciable amount of thermal energy through nuclear fusion. The energy which is produced by nuclear fusion occurs in core through a series of nuclear reaction which is called as proton-proton chain. This process converts hydrogen into helium. The core density is 150 times the density of water. So you can take an assumption that how much dense the core would be. Now we will move towards the next layer of sun, which is radiative zone. From the core out to about zero point 0.7 solar radius is the area occurred by the radiative zone from the core. Thermal radiation is the primary means of energy transfer here. The temperature drops from 7 million to 2 million Kelvin with increase the distance with core. The value of temperature gradient is less than the required. This is why thermal convection mode of transferring energy is not available here, and hence transfer of energy in this zone is occurred by radiation. Ions of hydrogen and helium emits photon which travel only a brief distance before being reabsorbed by other ions. Also, the density drops to 3 times that of coal in this radiative zone. Now, moving towards next the convection zone. The convection zone extends from zero point 0.7 solar radius, which is approximately 5 lakh kilometers near the surface of the sun from the core. In this layer, the solar plasma is not dense enough to transfer the heat energy in form of radiation, and hence this allows the convection currents to develop and moves the sun energy outwards its surface. The density of convective zone is comparatively very low, which is zero point 0.2 gram per centimeter cube. That's why the mass develops into thermal cells that carry majority heat outwards the sun photosphere above. At the photosphere, temperature drops to 5,100 kelvins, at, which I have discussed in the radiative zone. Thus, now we will move forward to next layers. Thus, it brings us to the next layer of the sun, which is photosphere. So, due to photosphere layer, we are able to see our sun through visible light. Otherwise, it becomes opaque. So, why we are able to see the sun through photosphere layer? So, this is because photons produced in this layer escape the sun through the transparent solar atmosphere above it and becomes sun radiations or sunlight or the solar radiation. The visible light which we see is produced as electron reacts with hydrogen atoms to produce H minus ions or H minus H negative ions. The photosphere layer is tens to hundred of kilometers thick and is slightly less opaque than our air on Earth. Thus, we can have a rough assumption that how much thick the layer of photosphere will be as compared to the air of the Earth. Since the upper part of photosphere is cooler than the lower part, an image of the sun appears brighter in the center than on the edge of the solar disk. Now, this leads us to moving the topmost layer, which is the atmosphere of the sun. So the atmosphere of the sun is the coolest layer of sun with minimum temperature region, approximately 4,100 Kelvin, with still a larger temperature, but relatively it is cooler than the other layers, and it is about 500 kilometers above the photosphere. During a total solar eclipse, when the disk of the sun is covered by that of the moon, parts of the sun surroundings, like atmosphere, can be seen easily. This part of the sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water. Atmosphere is further classified in different layers, which are the first, the chromosphere, the second, the transition region, the third, the corona, and the fourth, heliosphere. Uh, all these layers are amazingly much hotter than the other layers of the sun, which are the core, the radiative zone, photosphere, etc. In corona, solar winds took place due to which the flow of plasma occurs in the outward region of the sun into interplanetary space. So this leads us to the last and the final layer of sun, which is a technocline. Basically, it is not the final layer; it is the middle layer of the convective zone and the radiative zone. Technocline basically uh, separating the two layers, which is convection zone and radiative zone. So, so apart from layers of the sun, there are some events which are happened on sun's surface. So we are going to talk about these events. So the first event we are going to talk about is sunspots. So sunspots are basically the areas that appear dark on the surface of the sun. They appear dark because they are cooler than other parts of the sun surface. So why they are cooler, and they are cooler, they are relatively cooler than the sun layers. So they are cooler because the magnetic fields are particularly strong at that dark spots, and thus these magnetic fields are so strong that they keep some of the heat within the sun for reaching the surface of it. So now the second event, which is the most important event on sun's surface, is sun flares, or solar flares. So solar flares are caused due to the magnetic fields near the sunspot often tangle and cross and reorganize themselves. This can cause a sudden explosion of energy, which is called as solar flare. So solar flare creates a lots of radiation into space. If a solar flare is very intense, the radiation released can interfere with our radio communication here on Earth, and hence we can find that sun flares are or solar flares are occurring on the surface of sun. So this two events are important for us to understand because they are continuously being observed on the sun surface. Uh, Now I will show you animation of how magnetic field lines are reorganizing and tangling across each other in sun. You can see the sunspots which is displayed in the first image. the entangling and reorganizing magnetic field in the second image of the sun. And due to this, finally the solar flares, the explosions which are causing on the sun's surface in the third image. So this images will give you a brief idea about the main events of the sun surface. Without knowing the life cycle of sun or the formation of sun, our knowledge about our own solar system star is incomplete. So we will first learn the formation of sun. So the sun was formed about 4.6 billion years ago from the collapse of giant molecular cloud in itself. Now we have learned previously that giant molecular cloud does not collide itself. A triggering situation is required for it. So, why studies indicated that a triggering situation is occurred when one or more supernova must have occurred near the location where the sun formed. Thus, a shock wave from the nearest supernova would have triggered the formation of sun by compressing matter within the molecular cloud and causing certain region to collapse under its own gravity. Hence, much of the mass becomes concentrated in the center, which is core, whereas the rest flattened out into a disk that becomes the planets or other solar system of bodies. Thus, a giant molecular cloud is responsible for our solar system sun. And you can see in this image the yellow sun is the real image of the sun without the photosphere, without the visible light forming incident on the sun. The current situation of sun is represented by a scatter plot of xy in which x-axis is representing the age of sun in billions of years and the y-axis representing the ratio with current sun. The ratio is luminosity, radius and temperature. So as you can see the trend of graph, uh, as the age of sun increases, the luminosity and its radius increases and the temperature which will remain constant, and at the end of about 10 billion years it's becoming less. So sun is a G class main sequence star and hence its color is yellow. In each second, tons of matter are converted into energy within the sun core, which we have discussed earlier, and which is producing neutrinos and solar radiation. A sun with this rate will spend a total of 10 to 11 billion years as a main sequence star, and then the sun is gradually becoming hot during its time on the main sequence because of helium atoms occupy less space in the core than hydrogen atoms that were fused in the core. It is estimated that during 4.6 billion years, our sun becomes 30% more brighter than previous. As you can see in the graph, 30% more brightness is increased, luminosity is increased according to the trend, and it will further increase with the increase in the years. So the core is therefore shrinking and allowing other layer of sun to move closer to the center and experience a strong gravitational force with the increase in the years. So this is about the current situation of the main sequence G class star Sun, and now we will move towards the end of this Sun. How our Sun fuel exhausted. So now what will happen when there is not enough fuel that converts the hydrogen into helium and the hydrogen is exhausted? The sun is basically turned into a red giant and finally from red giant to a white dwarf. So the process is this: so the sun is considered as a low mass star, and since the mass is not enough for supernova explosion, the sun will exit as the main sequence star in approximately more 5 billion years from now and start to turn into a red giant. So now this red giant is processed into the post-asymptotic giant branch evolution, which is more even faster when no helium is also left for combustion for nuclear fuel to exhaust. And the luminosity stays approximately constant as the temperature increase in this evolution. Now this post-asymptotic giant branch evolution converts into asymptotic evolution with the ejection of half of the sun's mass into planetary nebula with ionized core, and thus the core temperature reaches 30,000 Kelvin, which is reduced from 15 million kelvins now, and it is finally converted into a white dwarf from planetary nebula. Now, when the white dwarf luminosity decreases with time, it takes billions of years to a white dwarf star to convert into a black dwarf with no luminosity in it. So this is all about our sun, its life cycle, its main cycle, and the fuel, and when the fuel is exhausted. So at last, I want to thank my friend Prabhanjan Kulkarni for helping me with this presentation. And if you like this video, please like, share, and subscribe the Astro Club FC page. And I think uh, this would be a wonderful experience to share the information about our sun, our star, and our galaxy with you. Thank you. And you can follow us on our Instagram and Twitter page for more updates of the talks and lectures by senior professor of this astronomy week.